Good afternoon, everyone. So today in this session, we'll be starting with the gravitational potential, right? And we'll be also discussing the gravitational potential energy. And later on, we'll be with the escape velocity and questions related to that, right? Now, the gravitational potential energy or the gravitational potential, it's defined as the gravitational potential at a point is defined as the amount of work done, right? In bringing a unit mass from infinity against a gravitational pull, right? To that point without changing its kinetic energy, right? Or we can say at each and every point, the mass is at equilibrium or the net force on the mass is equal to zero, right? Or we can say that the net kinetic energy of the particle is zero, or we can say that the particle is at every point the particle is in equilibrium or the particle is at rest, or we are slowly and steadily moving this particle from infinity to that point in a gravitational field, right? So that work done in bringing this particle from infinity to that point in a gravitational pull or gravitational field we call as gravitational potential, right? Now you can see here we have this particle of mass m, right? We are bringing this particle from infinity to the point P, right? Let's suppose this point is P here. Let's suppose this point is P here, and we're bringing this particle from infinity to this point P, right? Now the work done will be nothing. Let's suppose dW is the work done, right? So this work done will be where exerting a force, external force equal to the gravitational pull, so that the net force on this particle will be equal to zero, or this will be in consistent equilibrium, right? But the kinetic energy change will be equal to zero, right, for this particle, right? Now the force at a distance of force at a distance of x from this capital mass M is nothing, that will be gmm by x square, right? That will be gmm by x square, right? And the pull is against the displacement, right? That will be gmm x upon x square multiplied with the small displacement dx, right? So it's against the pull, that's minus gx, and cos of 180 degree, right? Cos of 180 degree. And the cos of 180 degree is nothing, that's equal to minus 1, right? Cos 180 degree is equal to minus 1. Therefore, the dW work is nothing, that's equal to gm m upon x square, right? Into dx. So this will be the work done, right? For displacing this particle from by a displacement of dx, right? To calculate the total work done to bring this particle from infinity at a distance of r or at a distance of x to the point P, we have to integrate it, right, from infinity to the distance x, right, to the distance x. So the total work done will be by the external force, that's W external, that will be equal to Gm, and m is a constant here, right? That will be integral of dx upon x square with the limits infinity to x, right? Now the integration of 1 by x square with respect to x is nothing. It will be equal to minus 1 upon x, right? The limits infinity to x, right? So substituting the value of limits, that will be gm m minus 1 upon x minus, that will be plus 1 upon infinity, right? And 1 upon infinity will be nothing, that will be equal to 0, right? That's equal to 0. So the total work done is nothing, that's W external, that is minus g m upon x, right? And this work done per unit mass, right? This work done per unit mass, that's W external upon for a unit mass upon m, that's equal to minus gm upon x, right? And this is what we call as potential, right? This is the gravitational potential denoted by V, right? So the gravitational potential due to a point mass, right, is minus gm by x, right? So this is the gravitational potential at this point P. So minus gm by x is the gravitational potential due to the point mass m, right, at a distance of x. So this is the gravitational potential at a point P due to this capital mass m, right? This is the gravitational potential. We know that to calculate the strength of the gravitational field, there are two ways to calculate the strength of the gravitational field. One is to calculate the gravitational field intensity, right? Another is to calculate the gravitational potential. So they directly measure the strength of the gravitational pull, right? Or the strength of the gravitational field at some point in a region, right? There are two quantities with the help of which we can predict or comment on the strength of the strength on the gravitational field. That's one, gravitational field intensity. Another is the gravitational potential, right? Now let's try to find the gravitational potential at the centroid, right? Now gravitational potential at the centroid will be the sum of the all the gravitational potentials. We know gravitational potential is nothing, it's a scalar quantity, right? It's a scalar quantity. It's a scalar quantity, right? It's a scalar quantity, right? So it means that gravitational potential because of n number of particles will be the a simple algebraic sum of gravitational potential because of each of the particles. Now you can see here we have three particles placed at the corners of an equilateral triangle, right? Three particles placed at the corners of an equilateral triangle, right? We have to calculate the gravitational potential at the centroid, right? So if the side of this triangle is and A, then this distance from the corner to the centroid of this triangle will be A upon root 3, right? So this distance R will be equal to A upon root 3. So A upon root 3 will be the distance. It means that the total gravitational potential will be because of the three particles, that will be minus Gm upon A by root 3, right? Plus minus Gm by A upon root 3, right? Plus minus Gm by A by root 3. So this will be the total potential at the centroid, right? Or we can say the total potential V will be equal to minus 3 times Gm upon A by root 3, or that will be minus 3 root 3 Gm by A. So this is the total potential at the point C, which is the centroid of this triangle, right? Now let's try to calculate this gravitational potential for this question, right? The question says there's two particles of mass m and 4m, right? We have two particles each of mass m, another of mass 4m, are placed at a distance or at a separation of 4 meters, right? At a separation of r, right? At a separation of r. Find the gravitational potential at the point where gravitational field intensity is 0. So we have to find the gravitational potential at a point where the gravitational field is 0, right? First of all, we'll try to calculate the point where the gravitational field intensity is 0 actually, right? Now you can see here, if we look at this point, the gravitational field will be along this direction, right? Let's call that as I1, and the gravitational intensity here because of 4m will be along the mass 4m. Let's call that I2, right? And for the gravitational field intensity to be 0, let's suppose at a distance of x from the mass m, the gravitational field intensity is 0, right? Then this remaining distance will be nothing, it will be r minus x, right? And these two gravitational fields or the gravitational intensity should be equal for the gravitational field intensity at this point P to be equal to 0, right? So I1 should be equal to I2, right? Therefore, I1 will be Gm upon x square, right? And the I2 will be equal to Gm upon r minus x whole square, right? Here the mass of this particle is 4, and we'll multiply by a factor of 4 here, right? Now Gm and Gm will get cancelled. We'll be left with 1 upon x square, that will be equal to 4 upon r minus x whole square, right? So that is r minus x whole square upon x square, that's equal to 4, right? So from here, we can just write it as r minus x upon x whole square, that's equal to 4, right? So the value of r minus x upon x will be nothing, that will be equal to root 4, that's 2, right? That's 2. So r upon x minus 1 is equal to 2, right? R minus x, r upon x minus 1 is equal to 2, right? Or r upon x is equal to 3, right? So from here, the value of x is nothing. That's equal to r upon 3, right? So this is the value at which this is the distance or the value of x at which the gravitational field intensity is equal to 0. That's r upon 3, right? Now at this point, we have to calculate the gravitational potential, right? We have to calculate the gravitational potential. So at this point, if the field intensity is 0, we have to find the gravitational potential. The gravitational potential will be nothing. It will be sum of the potential because of this mass m and the potential because of this mass 4m, right? The potential because of this mass m will be nothing. It will be minus gm upon x, where the value of x is r upon 3. So it will be minus 3 gm upon r, right? Then we will have gravitational potential because of this mass, and this distance from here will be 2r upon 3, right? It will be 2r upon 3. So it will be minus g into 4m upon 2r upon 3. So this will be the answer, right? So we'll be left with 3 gm upon r minus 3, or it will be 12 gm upon 2r, right? 2r. So we can write it as 6 gm minus 6 gm upon r, right? Or it's nothing, that's minus 9 gm upon r, right? So this will be the net gravitational potential at the point P. And at this point P, the net gravitational field intensity is also equal to 0. But the gravitational potential at this point is non-zero, right? Now let's look at this question. The question is find the potential at r if I is equal to k upon r cube, right? Now we have to look at the relation between the potential and the intensity, right? Where I is nothing, I here is the gravitational intensity, right? It's the intensity, gravitational intensity, right? We have to find the potential taking reference at infinity, right? Taking a reference at infinity, we have to find the potential, right? So the relation between the gravitational field intensity and the potential is nothing. The gravitational field intensity I is equal to minus dV upon dr, right? So this will give us the gravitational field intensity, or this is the relation between the gravitational field intensity and the potential, right? Now you can see here, if the value of V is a constant here, if value of V here is constant in a region or space, in a region or a space, in a region or space, in that region or space, the gravitational field intensity will be equal to 0, right? I will be equal to 0. So in a region or space where the gravitational field, gravitational potential is a constant, right? Then in that region or space, the field intensity is equal to 0. It means there will be no net gravitational field, right? Now, now in this question, we have been given that gravitational field intensity is present. That's k upon r cube, right? K upon r cube. We have to find the potential, right? So I will be equal to minus dv upon dr, right? That's equal to k upon r cube, right? K upon r cube, right? So if we integrate this on both sides, that will be minus k upon r cube, right? dr. We'll get to know about the gravitational field intensity, right? Now let's suppose at a position V, right? We At a position of R, we have the potential equal to V, and taking reference as infinity. So at infinity, the potential will be equal to 0. So we'll be taking the upper limit here, infinity, for the distance or the position, and the lower upper limit for the potential as a 0, right? Because if we take infinity as a reference for the finite mass distribution, right, then the potential at the infinite distance will be equal to 0 by reference, right? And let's suppose the potential at point potential as a function of v, or the potential at a distance r is equal to v, right? Now we'll integrate it, we'll get the value. Integral of dv, that will be v, that's 0 minus v, right? Minus k dr by r cube, right? Dr by r cube with the limits r to infinity, right? R to infinity. Now the value of this will be nothing, it will be minus k, right? It will be minus k. Integral of r cube will be nothing, it will be equal to integral of r cube will be r to the power minus 3, right, plus 1. That will be r to the power minus 2, right, upon minus 3 plus 1, right. That will be minus 2, right, with the limits r to infinity, right, r to infinity. So from here we get minus will be plus, it will be k upon 2, right, 1 upon r square, right. The limits are to infinity. The limits are to infinity, right. So the gravitational potential V will be here, that's minus V, right. That will be taking the upper limit, that's infinity, right. It will be 0, and the lower limit, that will be minus k by 2r square, right, minus k by 2r square. The potential is varying here as a function of position, that's k upon 2r square, right, k upon 2r square. So this is the value of potential at some point or at a distance of r, that's k upon 2r square, right. So the intensity is varying 1 upon r cube, the potential is varying as 1 upon r square, right. Now let's try to see the gravitational potential because of a spherical shell, right? Because of a spherical shell. The gravitational potential energy because of the solid sphere has been calculated in previous lectures, right? But in this lecture, we will try to calculate the gravitational potential because of the spherical shell, right? Now let's suppose this is the spherical shell. This is the spherical shell of radius r, right? Radius r. And mass of this shell is capital M, right? Now the gravitational potential because of this spherical shell, let's suppose at a distance of small r, right, outside the sphere, the gravitational potential will be same as that of the point charge, point mass, right, that will be minus gm by r, right. This is the potential outside sphere, right, outside shell, and the potential on the surface of the shell will be minus gm by capital R, right. This is nothing, this is the potential on the surface, right, on the surface. And the potential inside the shell, right, potential inside the shell will be the same, the potential on the surface of the shell, that's minus gm by r, right. That's a constant, right, that's a constant. So in case of shell, the net potential at each and every point inside the shell is same, right, and the value of this potential is nothing, v inside, that's equal to minus gm by capital R, right, minus gm by capital R, right. Or we can say the field intensity inside the shell will be given by minus dv upon dr, right. Since v here in this region is a constant, right, therefore we can say that in this region the gravitational field intensity is 0, right. So it means that there is no net gravitational field intensity. It means that if we place a mass m, if we place a mass small m inside the shell, right, if we place a mass small m inside the shell, then the net force on this mass will be equal to 0, right, because of the zero gravitational field intensity inside this spherical shell, right. So these are the values of the gravitational potential because of the shell on its surface, inside the shell, and outside the surface, right. So it's like a point mass, right, potential due to a point mass, that's gm by r, right, minus gm by r. Now let's talk about the gravitational potential energy, right. Now in the previous slides, right, in the previous slides, you can see we calculated the work done, right, work done in bringing a mass m from infinity to that point p, right. And the work done we got is nothing, work done we got was nothing, that was the minus gmm upon x, right, minus gmm upon x, right. And this work done is nothing, this work done is actually stored as the potential energy, right. This work done is stored as the potential energy, right. So this work done per unit mass, right, for the unit mass was called as gravitational potential, right. But the total work done here is stored as the potential energy, and this is called as the potential energy or the gravitational potential energy, right. So it's between the two masses, capital M, right. Let's suppose this is the mass capital M, right, and this is the point, this is the point mass at a distance of x, right, right, at a distance of x. It has been brought from infinity to this point P, right, at a displacement of dx, right. then the total work done here will be nothing. In bringing this mass m from infinity to the point P, that's GW, it will be nothing. It will be equal to Gm m upon x square, right? Dx, right? Dx. Now, if we integrate it, GW, right? Gm m upon x square dx with the limits infinity to x, right? Then this work done will be stored as the potential energy of the system, right? This work done will be stored as the potential energy of these masses, right? Potential energy, right? And this potential energy in case of gravitational field is nothing. It will be equal to minus Gm m upon x, right? So this will be the gravitational potential energy stored here, right? The gravitational potential energy in bringing a mass m from infinity to that point without changing its kinetic energy, right? And that work done we call as the gravitational potential energy, or this work done is stored as the potential energy of the system, right? And we know that potential energy is a concept where there is a conservative force, and gravitational force is a conservative force, right? The work that will be stored as the potential energy, right, between the system, right? So minus gmm by x will be the gravitational potential energy between the two masses, right? Now you can see here we have three particles, right? Three particles. Let's suppose we have three particles of mass m, m, and m, right? They are placed at the corners of an equilateral triangle, right? They are placed at the corners of an equilateral triangle. We have to find the gravitational potential energy because of this distribution, each of side A, and A, right? And the gravitational potential energy will be because of these two masses, right? M and M, M and M, and between these two masses as well, right? So the total gravitational potential energy, let's suppose it's denoted by U, right? Then the potential energy between these two masses, between A and B, right? A and B, between B and C, A and B, it will be minus Gm square upon A, right? And between B and C, it will be once again minus Gm square by A, right? And between C and A, it will be minus Gm square by A, right? So the total gravitational potential energy will be minus 3 times Gm square upon A, right? This will be the total gravitational potential energy between three particles, right? Which are placed at the corners of this equilateral triangle, right? Now, the similar question here is if the given system of three particles, right? Let's suppose this is the given system of the three particles in this question, right? Each of mass m on the vertices of an equilateral triangle side A is to be changed to side of 2A. Then find the work done on the system, right? It means that initially they were placed at the corners of the equilateral triangle with side A, right? Mass of each of these particles is m. Now, what is happening here that we are changing the side of the triangle from A to 2A, right? From A to 2A, from A to 2A. We're changing the side of the triangle from equilateral triangle from A to 2A, right? This is M, M, and M. Let's suppose the side of this triangle is 2A, right? 2A and 2A, right? Now, what is happening that because the side of the triangle has changed, right? Then the potential energy of the system will change. So the initial potential energy of the system will be nothing. That will be minus Gm square upon A, and there are three particles, so we'll multiply it by 3. So it means initial potential energy was minus 3 Gm square by A, right? Now, by changing the side of the equilateral triangle, the length or the distance between the two masses has changed, or we can say the potential energy of the system has changed, right? To change the potential energy of the system, we need to do some work on the system, right? Then only we can change the potential energy of the system, right? The final potential energy of the system will be minus 3 Gm square upon distance, right? Now the distance has been changed to 2A. We'll multiply here by a factor of 2A, right? Now the potential energy has changed. Now the change in potential energy, that's for you, final potential energy minus initial potential energy. This will be the work done required, right? This will give us the total work done in changing the system from A to 2A, right? Initially, the side of the triangle was A. Now the side of the triangle is 2A, right? So change in potential energy will give us the total work done, right? So this total work done delta W will be equal to final potential energy, that's minus 3 Gm square upon 2A, right? Minus initial, that will be plus 3 Gm square upon A, right? Now taking 3 gm square upon a as common, right? We'll be left with minus 1 by 2 plus 1, right? So it will be nothing. It will be 3 upon 2 gm square upon a, right? So this much of work is done in changing the system, right? From side A to side 2A, right? In case of equilateral triangle, where the 3 particles are placed at the corners of the equilateral triangle, right? So this is the work done, right? Now an object, now the question is that an object is projected from Earth's surface, right? We have an object, right? It has been projected from Earth's surface with speed u, right? And this speed u is under root of 1.5 gr, right? It's under root of 1.5 gr. Find the maximum height attained by object, right? It means that let's suppose we have this the Earth, right? This is the Earth, right? And from this surface or from the surface of Earth, an object has been projected, right? Object has been projected with initial speed that's equal to under root of 1.5 g multiplied by r, where r is the radius of this Earth, right? It's the radius of this Earth. Now the question is that this particle will move up, right, particularly upwards, right, and after some time this particle will attain its maximum height from the surface, right? Maximum height from the surface. Now we have to calculate this maximum height to which this particle can go, right, or the maximum height attained by the object, right? This we have to calculate, right? We know this field is a gravitational field. The particle is moving in a gravitational field. It's a conservative field, right? So the total mechanical energy will be conserved here, right? So total mechanical energy will be conserved here. Mechanical energy will be conserved, right? Will be conserved, or we can say we can use the conservation of energy, right? Conservation of energy, right? So initially it was projected. Let's suppose if we take the surface of this Earth as the reference, right? If we take the surface of this Earth as the reference, but this is the reference means the potential energy here at this point is taken to be zero, right? Potential energy at this point is taken to be zero, right? If this is the reference, right? Then at a height edge, right? This is the reference taken, surface of the Earth has been taken as the reference, right? So we'll take the potential energy at this reference as equal to zero, right? Now using the conservation of energy, right? So conservation energy is nothing. That's the kinetic energy initial plus potential energy initial. This must be equal to kinetic energy final plus potential energy final, right? Once this particle reaches the maximum height, its final velocity will be zero here, or we can say the kinetic energy final will be zero here, right? At this point, right? So at this point, the final kinetic energy for this particle will be zero, right? Final kinetic energy for this particle will be equal to zero, right? Initial kinetic energy was nothing, that was half. Initial kinetic energy was half m u square, right? The value of u square is 1.5 gr, right? That's 1.5 gr, right? And the initial potential energy with respect to the reference is zero, right? And the final kinetic energy is once again zero, right? And the final potential energy with respect to the reference will be nothing. It will be equal to minus gm m upon the distance. The distance with respect to the reference is h. Let me call it as h, right? Now, so it will be equal to 3 by 4 mgr, right? And 3 by 4 mgr, that will be equal to minus gm, right? Minus gmm by h, right? Minus gmm by h, right? This will be the potential energy initial, right? This is the potential energy final, right? This is the kinetic energy initial. This is the potential energy final, right? Now from here we can easily calculate the value of h, right? Now m and m will get cancelled. So we are only interested in the positive value of this h. Will just take mod here, right? We'll take the mod here. That's 3 gr upon 4, right? That will be equal to gm upon h, right? Gm upon h. We know the value of gm is nothing. It's equal to gr square, right? Gr square. It means that we can replace the value of gm here by gr square, right? Gr square upon h, right? That will be 3 gr upon 4, right? So from here, r and r will get cancelled, right? G and G will get cancelled. we'll get the value of h here equal to, that will be 4r upon 3, right? 4r upon 3. So the maximum height it can attain from the surface of Earth if it is projected with a speed 1.5 gr, right? And the maximum height it can attain is 4r upon 3. So this will be the maximum height attained by the object, right? Now let's discuss this question. A body of mass m kg starts falling from a distance to or above the Earth's surface. What is its kinetic energy when it has fallen to a distance r above the Earth's surface, right? Now you can see here, this is the Earth, right? This is the Earth here, right? A body of mass m kg starts falling from a distance 2r above the Earth's surface. It means that the distance of this object from the surface of Earth is given as 2r, right? The radius of Earth is r, right? It means the question says that when the object has fallen, right? When it has fallen to a distance r, right? It means the distance r it has fallen, the remaining distance will be r, right? The remaining distance will be r. Now we have to calculate the kinetic energy here, right? So at this point, P, we have to calculate the kinetic energy. What we will do is that we will once again conserve the mechanical energy, right? Conserve mechanical energy. So kinetic energy initial will be plus potential energy initial will be equal to kinetic energy final, right? Plus potential energy final, right? Now initially it was dropped, right? It was falling, or we can say the initial kinetic energy for this object was 0, right? Now initial potential energy for this object would be from the if we take the surface of Earth as the reference, it will be minus g m m upon 2r, right? That will be equal to final kinetic energy, right? Plus final potential energy, right? That's equal to minus g m upon r, right? So from here, the kinetic energy final will be nothing. That will be minus g m upon 2r plus g m upon r, right? So we get the value equal to g m upon 2r, right? So it's a plus, right? The kinetic energy will be always positive, right? So final kinetic energy will be equal to plus gm m upon 2r, right? So this is the final kinetic energy of this object, right? When it has fallen at distance equal to r from height to r, right? Now let's talk about the escape velocity, right? Concept of escape velocity, right? So concept of escape velocity is actually, now let's suppose this is the Earth, right? This is the Earth. This is the Earth. And the radius of this Earth is equal to r, right? And the mass of this Earth is capital M. Now, if we want to project a particle, right, at any angle, right? If we want to project a particle at any angle, right, in any direction, right, from the surface of Earth, right? Let's suppose we are projecting it with a speed of v, right? The particle is of mass m, right? So that this particle escapes the Earth's gravitational pull, right? Or we can say the particle moves to the infinite distance, right, with respect to the Earth's surface, right? So that there is no influence of the gravitational pull of Earth on this particle, right? So it will go to infinity, or we can say it escapes the gravitational pull of Earth. If it escapes the gravitational pull of Earth, right, so there will be no gravitational force because of the Earth on this particle at that distance, right? Or we can say the final potential energy of this particle will be zero because it's escaping the gravitational pull, right? It will escape the gravitational pull. It will have the final potential energy equal to zero, right? With respect to the Earth's surface, right? Now, now minimum kinetic energy required will be half mv square so that the particle will escape the Earth's gravitational pull, right? So the minimum velocity with which we should project this particle from the surface of Earth, right, in any direction, right? In any direction, we can project it here, right? We can project this particle here, right? Independent of the angle at which we are projecting it or the position we are projecting it, right, from the surface, right? so that it escapes the surface of Earth or it escapes the gravitational pull of Earth, right? This velocity we call as escape velocity or escape speed, right? So the minimum speed required to be given to a particle or body or an object so that it escapes the gravitational pull of Earth, right? And this velocity or this speed we call as escape velocity, right? Now to calculate this escape velocity, right, it means this if we project this particle from the surface of Earth, right, then at the infinite distance there will be no gravitational pull or there will be no gravitational potential energy because of the Earth, right? And it will just reach, so minimum speed required, right, is such that this particle just reaches the point where its gravitational pull becomes zero, right? And at that point the final kinetic energy, the final speed of this particle will be zero, right? Will be zero, right? At this point the final uh, velocity of this particle will be zero. Now, if we project this particle greater than the escape velocity, then definitely it will have some speed at this point P, right? But if we want to calculate the minimum speed, then at this point where the gravitational pull because of the Earth becomes zero, the speed of this particle should be zero, or the final potential energy of the particle will be zero, right? Now, let's try to calculate the minimum speed required, right? We can once again use the conservation of mechanical energy, right? Conservation of energy, right? Conservation of mechanical energy here. Conservation of mechanical energy can be once again used here, right? Now, initially, let's suppose from where this is the surface of Earth, right? And this is the center of Earth, right? With respect to the center of Earth, right? We're taking center as the reference, right? Taking center as the reference, center of Earth as the reference. Taking center of Earth as the reference, right? If we take center of this Earth as a reference, then potential energy of this particle with respect to the center, initial potential energy, that will be minus gm small m upon r, right? And the initial kinetic energy with which it has been projected will be nothing, that will be half mv square, right? Half mv square. Now the final potential energy will be zero because now the particle has escaped the gravitational pull of Earth, right? There will be no force because of the Earth on this particle, or the final potential energy because of the Earth will be equal to zero, right? And it just reached the point where the gravitational pull becomes zero. Then at that point, the particle will have a final velocity equal to zero, right? Final velocity equal to zero, or kinetic energy final will be equal to zero, right? Now applying the conservation of mechanical energy, right? So initial potential energy plus initial kinetic energy, that will be equal to initial final potential energy plus the final kinetic energy, right? Now initial potential energy as the value minus g m upon capital R, right? Plus initial kinetic energy, that's half m v square, right? V square, final potential energy is zero and the final kinetic energy is also zero, right? So from here we get the value half m v square, that will be equal to g m upon r, right? Gmm upon r. The m and m will get cancelled, or we get the value which is the minimum speed, and this speed we call as escape speed, right? And this escape speed is nothing, it's 2gm upon r, right? 2gm upon r. So the escape speed required, minimum speed required for the particle to be projected from the surface of Earth so that it escapes the gravitational pull of Earth, that's under root of 2gm by r, right? Under root of 2 gm by r. We know the value of g at 6.67 into 10 to the power minus 11. The mass of Earth at 6 into 10 to the power 24. And the radius of Earth is 6,400 kilometers, right? If we substitute these values, the value of escape speed approximately comes out to be equal to 11.2 kilometers per second, right? So it means this speed, this should be the speed of this object, right? With this speed, the object should be projected from the surface of Earth so that it escapes the Earth's gravitational pull, right? So it's a very large speed, a very huge speed, right? So this is how we can actually project an object, right? If any speed which is greater than escape speed, it's for sure that the particle will escape the gravitational pull, right? But this is the minimum speed required, right? So as to particle escape from the surface of Earth, right? Now we can replace this gm by, this is for any planet, right? This is by for any planet under root of 2 gm by r. Now for the Earth, uh, we can replace this gm by small g r square, right? So it means that we will have the escape speed or escape velocity equal to under root of 2gr, right? Under root of 2gr. So for any planet, we can use this equation, right? For any planet, we can use this equation, right? That's under root of 2gm by r. But for Earth, specifically, we can use both the equation, right? But here, small g is the acceleration due to gravity. It's only acceleration due to gravity on the surface of Earth, right? So that's why we'll be using this equation on the surface only, right? On the surface of Earth only. So this is the concept of the escape velocity, right? Now let's try to solve the question on escape velocity, right? An unknown planet is of twice the mass and half the mass of Earth, right? Twice the size and half the mass of Earth, right? If escape velocity from Earth's surface is V0, what would be escape velocity of particle from the unknown planet, right? So we know escape velocity is nothing that's under root of 2gm upon r, right? This is the escape velocity, right? If this is the escape velocity, we can see here the escape velocity is actually proportional to root of m upon r, right? Where m is the mass of the planet and r is the size of the planet, right? By size of the planet, we mean the radius of the planet here, right? So we can say here VE1 upon VE2 will be nothing. It will be under root of m1 upon m2 multiplied by under root of r2 upon r1, right? So this will be the ratio between the two escape velocities, right? For two planets, right? So the escape velocity of first first planet is given as V naught, right? We have to calculate the escape velocity of second planet. And unknown planet is of twice the size. So R2 is 2 times R and half the mass of Earth, right? So M2 is M by 2, right? If this is M, then M2 is M by 2, right? And R2 is twice R, right? Twice R. So it means that R and R will get cancelled, M and M will get cancelled. Root 2 multiplied by root 2 is nothing, that's equal to 2, right? So escape velocity of second planet is nothing, it's half of the escape velocity on the surface of Earth, right? So V naught by 2 will be the final answer for this question, right? This is how we can compare the escape velocities of two planets, right? Now let's talk about the escape velocity. Another question: density of Earth becomes twice without changing its radius, right? How much will its escape velocity become, right? Now, how the escape velocity will change upon changing the density of planet, right? Now you know that the escape velocity is nothing; it's equal to under root of 2gm upon r, right? 2gm upon r. The density d is defined as mass per unit volume, right? Or we can write it as m upon 4 upon 3, assuming the Earth to be a spherical in shape, right? It will be m upon 4 by 3 pi r cube, right? So V escape will be here. That will be under root of 2gm, right? Replacing m by density multiplied by the volume, right? Density is d and volume is 4 upon 3 pi r cube, right? Upon r, right? Now this r and r will get cancelled, right? Will be left here with under root of 8 pi upon 3, right? G multiplied by density into r square, right? R square. So from here, if density of Earth becomes twice without changing its radius, right? If the density of Earth will become twice without changing its radius, the escape velocity will be proportional to under root of density, right? Under root of density. So it means that V2 upon V1 will be nothing. It will be under root of D2 upon D1, right? D2 upon D1. Now the density has become twice. It will be 2D and D here, right? So the new escape velocity will become root 2 times the initial escape velocity, right? So it will become root 2 times, right? The new escape velocity will be root 2 times, right? Without changing the radius, right? So that's it with respect to the escape velocity and all, right? And there is a small topic left, right? That's the satellites or the orbital speeds or the orbital velocities, right? Of satellites and Kepler's laws of planetary motion, right? That will be discussed in the next lecture. Till then, take care and goodbye.